Hello everyone, welcome to Computer Organization and Architecture class. In this unit, we will talk about assembly language instructions and addressing modes. On the screen is a simple assembly language program fragment using the LD, ST, and ADD instructions. This code fragment is equivalent to the Java statement z equal x plus y. As you can see on the screen, the yellow blocks represent registers, where the symbols at the bottom indicate the register ID. The blue blocks on the right represent system memory. The numbers inside the blue block are values stored in the memory. The numbers on the right indicate the memory address in binary and in decimal format. Assume the memory address of the variable x is 0011. The memory address of the variable y is 0101. And the memory address of the variable z is 0111. When executing the first statement, LD x, register 1, the value 0010 stored in memory address 0011 is loaded to register 1. When executing the second statement, LD y, register 2, the value 0111 stored in memory address 0101 is loaded to register 2. When executing the third statement, add register 1, register 2, register 3. The values in register 1 and register 2 are added, and the sum 1001 is stored in register 3. When executing the fourth statement, ST, register 3, Z, the value 1001 stored in the register 3 is then stored in the memory address 0111. In control instructions, the call and jump L instructions form a pair that are used in calling and returning from a subroutine, respectively. Jump L is also used to transfer control to another part of the program. For example, assume you are running program A and need to call subroutine B stored in memory address B. In the program A, the statement call B will transfer the control to subroutine B and start executing subroutine B. After executing the subroutine B, the jump L instruction transfers the control to program A and continue executing program A. Similarly, assume subroutine C stored in memory address C In the program A, the statement call C will transfer the control to subroutine C and start executing subroutine C. After executing the subroutine C, the jump L instruction transfers the control to program A and continue executing program A. Subroutine, also known as function, procedure, or method, is a sequence of instructions. When a subroutine is called, the input arguments must bind to values stored in the system memories. For example, assume we create a subroutine named sum, which takes two input arguments stored in variables a and b respectively. The variables a and b indicate the memory addresses. Thus, when the function sum is called, the values stored in the memory addresses a and b will be passed to the subroutine for calculation. The sum of the two values will be returned to the caller and stored in memory address C. Calling a subroutine relies on the system stack to manage the control so that when the subroutine is finished, the control will return to the caller. There are two different ways to pass input arguments. The first approach is pass by value, and the second approach is pass by reference. Pass by value indicates the value stored in the provided memory address is passed to the subroutine and stored in a new memory address. Pass by value can be considered as sending a document to the subroutine by fax, so that the subroutine works on a copy of the document. Pass by reference indicates the memory address of the value is passed to the subroutine so that the subroutine works on the memory address directly. Pass by reference can be considered as sending the original document to the subroutine so that the subroutine works on the original document. As you can imagine that if a document has a lot of pages, such as an array, it is inefficient to send all pages to the subroutine by fax. Therefore, it will be more convenient to send the original document to subroutine. For this reason, when passing an array to subroutine, pass by reference is used. The ARC architecture has just a few instruction formats. In the instruction word, the two most significant bits, that is, the OP field, is used to define the four primary operations, including setHI and branch, call, arithmetic, and memory. Additional bit fields OP2, OP3, and cond in the rest of the instruction word completely define the instruction. In addition to the ARC instructions that are supported by the architecture, there are also pseudo operations. Pseudo operations are not OP codes at all, but rather instructions to the assembler to perform some action at assembly time. A list of pseudo operations and example of their usages are shown on the screen. Many assemblers will accept synthetic instructions that are converted to actual machine language instructions during assembly. We show some commonly used synthetic instructions on the screen. The left column is a synthetic instruction. The middle column is the instruction generated, and the meaning of the synthetic instruction is shown on the right. In order to access data in memory, there are 5 different addressing modes, including first, immediate addressing, which allows a reference to a constant that is known in assembly time. Second, direct addressing, which is used to access data items whose address is known at assembly time. Third, register indirect addressing, which is used when the address of the operand is not known until runtime. Fourth, register indexed addressing, which is used to access components of an array by adding the index to the base address. Fifth, indirect addressing, which is used to access a pointer variable whose address is known at a compile time. This mode is seldom supported in modern processors. Any questions?